Good afternoon. Welcome back to Saudi Mobile Show AI conference. Our next session will be on detecting and handling cyber attacks via neural network based control algorithm for industrial application, presented by Dr. Fahad Albalawi. Sir, please continue. Hello and welcome everyone. Good
Yes.
afternoon. So please continue.
Hello.
Hello and welcome everyone for the session. Dr. Fahad Al-Balawi will be talking about detecting and handling cyber attacks via neural network-based control algorithm for industrial application. Sir, please start.
Yes. Okay. Thank you. Okay, for your introduction. So today I'm gonna present a recent research work that was published in 2019 and is entitled as "Detecting and Handling Cyber Attacks via Neural Network-Based Control Algorithm for Industrial Application." So the outline of the talk will be as follow. First, I will give some background on what type of cybersecurity that I am targeting and what I want to talk about exactly. Then I will jump to talk about the proposed framework that integrate the neural network detection algorithm with the advanced control technique, which is called model predictive control, that can handle a specific type of physical cyber attack and mitigate it, and then apply the control action that is calculated by the MPC to maintain and guarantee the closed loop stability and hence the process operational safety of the process. And lastly, we will apply this algorithm to a real application, which is a chemical batch process, where we can illustrate the proposed algorithm. So let me just go here. So for those who are not familiar with the cyber attacks or what they talk about today, which is the physical cyber attack, is actually physical cyber attacks can be defined as a series of computer actions that can hit chemical plants so that the plant operation will be jeopardized. And this can be realized by hitting different elements within the process control system. For example, it can hit PLCs, which is the programmable logic controllers, or sensors to play with the state measurements. So the controllers will take a false control action because they read falsy measurements. And so to emphasize the importance of this, I'm just posting here a very recent incident that hit one of the Saudi refineries back in 2017, which is published in New York Times, where a special type of or a malicious type of cyber assault uh, hit a chemical plant where exactly it hits a process sensors to play with the sensor measurements so the control action will increase the pressure in some of the pipes. But luckily, the process safety and the control system was smart enough to act in a proactive fashion so that unsafe scenario will be prevented. So this scenario and many different incidents that happens, or thousand or million incident that happens daily basis for nationwide or internationally because of these malicious attack, emphasize the importance of developing detection algorithm that can predict the occurrence of this attack and make a proactive action to prevent the impact of this attack on the plant operation. Sorry for that. So, as I said before, the importance of this is can be realized because it can jeopardize the plant operation and hence the process operational safety, which will damage the environment and sometimes go to the unstable production, human injury, maybe sometimes human death due to this cyber attack. So what can we do? So what we can do is to propose a novel or intelligent detection algorithm that can understand the mind of these attackers And then this detection algorithm can be employed online, and it's integrated with control frameworks that can take benefits of the detection result of this attack, and hence apply control action that can proactively maintain the closed loop stability and safety in the presence of these attacks. So physical cyber attack are a it's a huge topic actually. So and physical cyber attacks are of many types, but just the focus on three types, which is denial of service attack and replay attacks and deceptions attack. Our focus today in the talk, due to the limitation of the time, we will talk about only deceptions attacks, and more specifically, it's a specific type of it. It's called min-max cyber attack that I will go in detail with it later in the slides. But just to give you a brief, give you a brief knowledge about it, is the type of attack that hits the sensors within the control system, so that it can make it read the minimum value or the maximum value of the sensor, so that the controllers wouldn't um, recognize these false measurement, and hence apply control action based on these false measurement, and this may lead to unsafe scenario and some to explosions if these attack were not detected. Of course, in the literature and in industry, different detection algorithms have been proposed to overcome this attack. And basically, we talk about model-based one, like the cumulative sum statistic detection algorithm. And sometimes we talk about probabilistic based one, like the Bayesian detection and binary hypothesis. However, these detection algorithm were successful in real-time implementation, but with numerous amount of the technological advances of abilities and facilities for the attacker to make them know about these model-based detection algorithms and the probabilistic ones as well, make it hard for the industrial plants operators and decision makers to cope with this intelligence of the attackers. So one could think of a more generalized detection algorithm that can be applied online and can detect a new type of attack so that we can cope with the attacker thinking. So motivated by this consideration, we will talk today about a specific type of integration of a machine learning based classification algorithm that can be integrated with an advanced control technique that is based on optimization framework that can work together to maintain the closed loop stability and process operational safety in the presence of these cyber attacks. And I will go in more details about how we can do that, but without bothering you with the technical stuff of the element. So, of course, before we go dig deep in the analysis of this, for those who are not familiar, we should give some preliminaries about what class of system that we are talking about, and to what extent our limitation go to. So the class of system is actually a nonlinear or differential equations that can be written in this format, where f is the vector function of the process and g is input. Where u is the input, and g of x is just a function of the states that couple the input with the states, and w demonstrate, or w here it's denote or capture the mismatch between the process model that we use here and the actual model of the process that we don't know exactly. So we have to put a notion that can capture this uncertainty. So U is the manipulated input that we control. Of course, it's constrained due to the physical constraint, the actuator, because our valves and our pump are constrained physically, because we cannot open the valve, for example, more than 100%. We cannot close it less than 0%. So the most important assumption that we have to emphasize here for this framework is as follow. We assume that the vector function f, g, and r smooth function that can help us to define a stability control law. The measurement, here we assume that we have an access to the measurement of the process. So we don't assume here that we don't have an access to the measurement. In such a case, then we will need an observer that can observe the states. We assume also that the origin is the equilibrium point of the process. And lastly, we assume the existence of a control law, which is a Lyapunov-based one, that can make the energy of the energy of the process negative, which is the lead derivative of the Lyapunov function with respect to the process model is negative. So here in this slide, we will take maybe 1 minute to talk about the advanced control technique that called model control. And as the name suggests, the model-based control uses a model of the process in order to predict the future of the evolution of the process state, so better control action can be taken. MPC is an optimization control paradigm where the cost function here is a quadratic cost function that tries to penalize the deviation of the state and the input from their corresponding set points. Here in the constraint, we have the process model, as you can see, to predict the evolution of the states so we can have a better action. As a life, for any one of us, like if we predict what we can do in the future, then we can prevent unsafe scenario, then we can plan ahead, then we can take a better action with the same concept, with the same sense happening in industry and in the control system. So we predict the evolution of the state, then better control action can be taken using this optimization algorithm. So this indicates that the initial state of the process is actually the major state of the from the plant, and this is the place where the cyber attack affects the controllers, as you can see, because this major state comes from the sensor. So if the sensor was tampered or played with from the attacker, then the whole control actions will be affected. Then we have the input constraint due to the physical constraint in the actuator, as we said before. As you can see here, excuse me. As you can see here, the red colored and the blue colored constraints are defined as stability constraint, where the first one tries to decrease the energy of the system in a degree that is as minimum as the degree offered by the control law 5x. And here we maintain that if the state enters the stability region omega rho min, then we want to make sure that we are inside it for the rest of the time. So this is just a brief definition, and you can see here in the schematic figure that the big ellipse is the stability region, or what we call the stability region is in the other sense is the operating region, as if the plant is allowed to operate in a region where the states can vary within this big ellipse. However, we want to make sure that the state go to a certain small neighborhood of the origin, which is XS in this case. And that's why we apply the MPC, because most of the cases we want to operate around a certain steady state like XS. And we don't want to deviate from it because we believe this is the optimal set point that we can operate. So therefore, we want to go to it and we want to close ourselves around the region around it for the rest of the operation until a new set point comes ahead from the upper layer of the management. Sorry. So here is the slide that I promised you to talk about the specific type of deception attack that I was talking about, which is the min-max cyber attack. Min-max cyber attack is designed to tamper the sensor management. To tamper its measurement with the maximum and minimum allowable value, as you can see in this equation, which is very easy to read, even for those who are not familiar with the control system. And I carried it with you here. So X bar is the tampered or the played with measurement from the attacker. So either he set the value to the minimum value or the maximum value of the allowable value that the state can take within the stability region. Let me go back to the slide here so I can show you what I mean. So if this is the stability region, which is the big ellipse, then the maximum value that the state measurement can take is at the upper boundary of it, and the minimum value could be at the lower value. So what basically the attacker would do is set the value to the minimum value or the maximum value. So in order for the attacker to take such action or to attack in such sense, we have to assume that the attacker has the following knowledge. We assume that the attacker have full knowledge of the stability region, otherwise he cannot know the maximum and the minimum value of the states that can take. We assume that the attacker can get access to the sensor itself to play within its measurement. However, the process model knowledge does not have to be there for the it has not to be there for the attacker to take. So that's which is very powerful. So the attacker does not have to know the process model. He just needs to know the stability region that we operate at. Then he can go further with that. Sorry about that. So in this slide, we will talk specifically about what kind of machine learning that we are using. We're basically talking about a neural network, not a deep one. We can go with 1 or 2, 3 hidden layers, which is more than enough in our case. We have to generate the data set that can help the neural network to classify based on the state measurement that we are under cyber attack, or we under normal operation, or we under disturbed attack. How can we do that? Basically, we can do the following. We use the process model of the system to generate 3 data sets. A set where we apply a min-max cyber attack by just playing with the measurement sensor, and then we call this class 0. Then we, in the other case, we just operate normally. There is no cyber attack and there is no disturbed operation, no Gaussian added noise, and we call that class the normal states. And then we operate the system under Gaussian noise that we added on the right-hand side of the ordinary differential equation to mimic the mismatch between the process. Why we need a third class? Why just we're not happy with 2 classes, which is under cyber attack and no cyber attack? Because sometimes white Gaussian noise are not an intended attack, and we don't want our detection algorithm to be fooled by not distinguishing between the cyber attack and the natural disturbance of the system, because then it will give us a false alarm of cyber attack that were not happening. Okay, so of course, with all your familiar with the AI, I wouldn't go deep in talking about how a neural network works and so on. I'm not the best guy to talk about this, but you know, I hear what we mean by sigma 1, sigma 2 is the activation function that could be sigmoid, reload functions. It's option your choice. Then we can tweak these based on the result and what kind of accuracy that you're looking for. NWIG is the weighting that you update every time you iterate. And NBI is the bias that you have. The output layer, of course, you can have different activation function, which is a softmax at the output layer to give you the decisions whether you are under which class. Okay, so this is very important in our framework, as this indicates we don't want our detection algorithm to be very reckless in deciding which class it's under to. So for example, we want to reduce the false detection alarms or the false cyber attack alarm, because these networks are not perfect and they are subject to different noises, and it cannot give you always the right thing. So I'm not sure if someone is writing in the slides. Is everything okay? I'm not sure.
No, I think we need to go out and come back again. There is something wrong here. Yes. يعني إشكال الأخلاقيات جاية مع الذكاء
الاصطناعي. Sorry, I couldn't understand what's going on.
I think someone with us got into hacked or something, hacking the system. Maybe we should just go out and come back again.
I'll say then should I